Okay, so let's start the tutorial. So this is a tutorial on energy-based machine learning. So my name is Takayuki Osogami, and I'm going to give this tutorial with Sakya there. And we are both from IBM Research at Tokyo. So these are the topics that we're going to cover today. Part 1 and part 3 are going to be covered by me, and part 2 and part 4 will be covered by Sakya. So we have a break from 4 to 4:30. And so the first two parts are for 2 hours, and the last two parts are for one and a half hours. But we plan to start part 3 before break. And we stop at 4 sharp, and then resume part 3 after the break. So before going into the details of each part, we want to start from the highlights from each part. So, in the first part, I'm going to talk about Boltzmann machines and energy-based models. So we're going to see that there are beautiful mathematical expressions for the gradient and Laplacians for Boltzmann machines, and these are gradient-based learning rules actually give some theoretical foundation on Hebb's rule, which is known for some brains. We're going to see several objective functions, and in energy-based models, it is important that we have this. We're going to see some contrastive terms, which is important, and we're going to see these contrastive terms are derived from various objective functions, such as the K divergence, contrastive divergence, and feature divergence, which is also known as score matching. And I'm going to also talk a little bit about recent work on energy-based generative adversarial network, but otherwise, much of the contents in part 1 is sort of classical.
Okay, so we are just changing the speakers to make sure that you'll get used to 2 different speakers and 2 different voices speaking. So the second part basically is going to be a historical perspective, largely things that probably many of you already know or have used. Essentially, we'll focus on restricted Boltzmann machines, defining what an RBM is, as compared to the first part where we would have talked about more general Boltzmann machines and energy-based models. And we'll also look at some of the deep variants like deep belief networks and deep Boltzmann machines, and using approximate procedures like contrastive divergence and variational inference.
In part 3, going to be some topics on Boltzmann machine for time series learning. So we're going to see some successful applications in time series of structured patterns, and these examples are in human motion modeling and music. So we're going to also talk about dynamic Boltzmann machine. This is particularly suitable for online learning of time series modeling, time series learning. So we're going to see that the learning complexity in per step complexity is constant, which is in contrast to linear time complexity for backpropagation through time. We're going to also see some relations to some interesting spike timing dependent plasticity, which is a refinement to the Hebbian learning rule. We're going to also talk about some recent work on the extension of dynamic Boltzmann machines, including the one that we're going to be presented in this conference.
And finally, in part 4, we'll see some applications and theories behind using energy-based models for reinforcement learning. So different problem setting. So first 2 parts would have, or first 3 parts would have really concentrated on generative models and prediction as a problem. And in the 4th part, we'll see how to use reward-based or learning with feedback when we want to learn some kind of actions of agents. And we'll introduce so we'll have an historical perspective of using the energy of restricted Boltzmann machines as a function approximator for reinforcement learning. And then we'll move on to some of newer methods, like dynamic Boltzmann machine, how to use the energy of this dynamic Boltzmann machine, which Osogami just talked about. And we'll also see some uses of policy gradient methods, and not just value function approximation reinforcement learning, but also policy gradient methods and how they are much more efficient. And finally, we'll finish with some perspectives on deep reinforcement learning using these energy-based models.
Okay, so we have made this presentation materials online at our tutorial webpage. And actually, our webpage is quite easy to find. If you Google IJCAI17, our webpage comes next to the IJCAI homepage. Okay, so then let's start from part 1. So part one is on Boltzmann machines and energy-based models. So we're gonna start from some basics of Boltzmann machines. So for this part, this morning I have just published a research technical report, which is called the same title as part one. And you can find a link to this research report from our tutorial webpage as well. It's a 36 page, it's quite long paper, but it has all derivations, not all, but pretty much all derivations that I want to talk about today. So let's start with some definitions and some basic properties of Boltzmann machines. Okay, so Boltzmann machine consists of a set of units and the connection between those units. So each unit takes some binary values. So Boltzmann machine can be used to define a distribution over binary patterns. So there are two types of parameters. One is called bias. Bias is associated with each unit, and another parameter is called weight, and the weight is associated with each connection. So given this, the value of the parameters and the value of the variables, we can define an energy of the Boltzmann machine. And for a Boltzmann machine, energy has this simple expression here. So given this energy, we can define a probability distribution over the binary patterns, and which looks like this. And here, the summation over, with respect to tilde x, it means that we take summation over all possible binary patterns that this Boltzmann machine can take. So this is a general expression for energy-based stochastic model. So whenever you define some energy, and then we can talk about some probability distribution using this energy. So in this talk, so we're going to talk about generative learning and discriminative learning with Boltzmann machine or energy-based models. And when I say generative learning, it means that we learn the distribution of the patterns. So we get some target distribution of patterns, and we try to model this try to fit this distribution with the distribution defined by the Boltzmann machines. So this means that we want to find a theta, parameter of the theta, such that distribution defined by Boltzmann machine best approximates a given target distribution. So I'm going to specify what we really mean by best approximation. And when I say discriminative learning, it means that we're going to fit a conditional distribution of the output distribution given input. So in this case, so we have a Boltzmann machine here, that some units of a Boltzmann machine are associated with input, and some units are associated with output pattern. And there are also some hidden units that are not associated with input or output. So here the goal is to find a theta such that this conditional distribution best approximates a given target conditional distribution. And again, I'm going to make it clear what this really means. So let's start with generative learning. So to define some learning, we need to start with some objective function. So the standard objective function in generative learning is to minimize the k divergence to the target distribution. So it has this mathematical expression. And because this first term is independent of the parameter theta, so we just need to maximize the second part, or minimize the second part, or maximize this part without this negative sign. So our objective function looks like this. So it is a log probability, expected value of log probability, where the expectation is with respect to this target distribution. So when the target distribution, sometimes target distribution is given implicitly by as samples from this target distribution. So let's say that the data D is samples from some unknown target distribution, and then this let this target distribution be an empirical distribution given by the data. Then this f theta becomes an expression like this. So this is to maximize the log likelihood of the data. So minimizing Cayley divergence is equal to maximizing the log likelihood. So we use both words interchangeably. So once we define an objective function, a learning rule can be derived by just looking at the gradient of this objective function. So the gradient of this objective function can be given by this one. So what we need is the gradient of log probability of some patterns. And once we get this gradient, we can iteratively update parameter theta with this expression where eta is a learning rate. So let's look at the specific form of the gradient of this log probability. So, and we're going to start with a very simple case where there are no hidden units. But I think it is still interesting and gives some intuition about energy-based learning. So the gradient of the log likelihood when there are no hidden units can be expressed like this. So there are two terms. So the first term is the expected gradient of the energy, where the expectation is with respect to the target distribution. So this term tries to reduce the energy of the patterns that appear frequently in target distribution. The second part is expectation of the gradient of our energy, where the expectation is with respect to the model distribution, which is our current estimate of the distribution. So this means that the second term tries to increase the energy of the patterns that the current model generates. And this term is called a contrastive term. This term, we will say that this is a contrastive term in energy-based learning. So we can further represent this gradient, which looks like this. So this is then this is an expectation with respect to a target distribution. And so expected value of this one. So because this is expectation with respect to a target distribution, it implies a stochastic gradient method of first sampling a pattern from the target distribution and use a stochastic gradient to define this pattern to update the parameters. So I use x omega to denote a sample from some distribution. In this case, the sample is taken from this target distribution. And the sample is used to compute this gradient of energy. So this is the gradient of energy of a sampled pattern. And this is still, so this x is still a random variable. So this is still expectation of the gradient of energy, where the expectation is with respect to a model distribution. So this stochastic gradient rule can be illustrated with this figure. So suppose that this is a sampled value. And so this stochastic gradient rule says that we should reduce the energy of this pattern, but increase the energy of the other patterns that they are like this. So, and this kind of rule, which reduces some energy and increases some other energy, appears frequently in this talk. So far, this expression holds for all energy-based stochastic models. But when we look at this specific energy-based model of Boltzmann machine, we have a much simpler expression. So the energy function of Boltzmann machine looks like this. So it is the linear in here, and this is quadratic here. So the derivative with respect to a bias has this expression, and the derivative with respect to a rate has this expression. So plugging this expression into our general gradient expression, we get this simpler form. So what is so let's just look at this stochastic gradient for the weight update rule. So it says that when xi and xj takes both 1, so remember that x takes binary values. When both values are 1, we should increase wij. But if one of them is 0, we should decrease wij by this amount. And this learning rule has an interesting relation to Hebbian learning rule, which is known in neuroscience. So Hebb's rule says that neurons essentially says this. So neurons that are wired together, neurons wired together if they fire together at the same time. So each unit in Boltzmann machine is like a neuron, can be associated with a neuron. And when both unit takes value 1, which means that both neurons fire together, then it says that we should increase the weight by this amount. Well, what is equally important is actually this second term, which is nothing to do with Hebbian learning rule. But it said that we don't update this Wij so much if it is already expected that these two units fire together. And without this second term, the learning actually diverges. So if that diverges. So just mimicking just heuristically mimicking Hebbian learning rule just goes to divergent learning rule. But because this is a learning rule that is derived from a stochastic model, which is a Boltzmann machine and an objective function, this learning rule actually maximizes this objective function. So, so if you look at we can take the gradient again to look at the Laplacian. And it turns out that Laplacian has a very simple form of this covariance. So I couldn't find, because this can be expressed as a covariance, we can immediately see that the objective function is concave. And this is when all units are visible. I couldn't find this particular expression in the literature, but in my technical report, I have all the derivations. But if you know that this particular, so I know that this is a known result, so maybe some obvious step, but if you know that this is known in some other literature, please, it would be great if you let me know. So this page summarizes what we have seen so far. So this is the generative learning when all units are visible. So in this slide, I defined a new notation S. So S consists of all monomials of degree up to 2. So x1 through xn, and this product of x1, x2 to this. And with this expression, a gradient can be expressed like this, and the Laplacian can be expressed like this. This covariance is a covariance matrix. So it has a very simple form. So, so if you have any question, please ask during the talk. If the question is really to help you to understand the material. So if your question is sort of more like a discussion, please postpone it until the end of each part or the end of the tutorial. Right. So let's go to a more general case when some of the units are hidden. So I first want to start with why we need hidden units at all. But it becomes quite obvious that if you count the number of parameters in the Boltzmann machine with n units, this is to represent the distribution of n-bit binary values. We have only this much parameters. But the general distribution for that represent n-bit patterns need to assign probabilities all of these patterns. And because we also need to normalize it so that the probability to sum up to 1, we have this amount of, we need this many parameters to describe the general distribution. So we have this exponential gap. So we need hidden units. So in the second part, we will see that restricted Boltzmann machine is actually a universal approximation. So let's start with a definition of Boltzmann machine when we have hidden units. So there aren't many changes from the case without hidden units, but energy has this expression where x denotes visible values and h denotes hidden values. So we still have this linear form and this quadratic form. The probability over all visible and hidden patterns hasn't changed as this energy-based general expression. But what we are interested in is this marginal distribution over visible patterns. So we have this summation over all hidden values. So it turns out that it is convenient to define a new quantity called free energy. So free energy is defined as this. So this is a log of summation of exponential minus energy, where the summation is over all possible binary hidden patterns. Once we define this free energy, we can express this marginal distribution of visible values using this form, which is the same form as this one, which is for when all units are visible. We just need to replace energy with free energy. So to derive a rounding rule for this case, we need a gradient of the free energy, because in this case we just need the gradient of the energy. So the gradient in this case looks like this. So again, it consists of two parts. So it is expectation with respect gradient of the free energy with respect to a target expectation with respect to target distribution. And second term is a gradient of the free energy, but the expectation is with respect to the model distribution. So we can express this expression using the energy, and then it looks like this. So still, the first expression is expectation of the gradient of the energy, but expectation is with respect to the target distribution of the visible values. And for the hidden values, we use conditional distribution defined by our model, because there is no target distribution for hidden units. This expectation with respect to this model distribution hasn't really changed. We just need to consider hidden variables as well. So again, it suggests a stochastic gradient method, and so we can express this using the expected value expectation with respect to target distribution. So we just need to take a sample from a data, which is x omega, and compute a stochastic gradient. But now the stochastic gradient are changed a little bit. And here the only change is that for hidden units, we use conditional expected value given these visible values. So I always use x omega to denote sampled visible values, and h to denote random, capital H to denote random hidden values. So this is expectation with respect to model distribution. But the expectation is over this. Expectation is with respect to a conditional distribution over hidden values given these visible values. The second term don't change at all. So the specific form of the stochastic aptitude for a Boltzmann machine looks like this. So so again, the only change is that so this is the same as the case when we have only visible units. So when we have hidden units, so we'll say that J is hidden, we use this conditional expected value for hidden units instead of given values. So otherwise, nothing has been really changed. So again, we can take the gradient again to get a Laplacian, which again has a nice expression. So this time, the second derivative looks like this. This is a covariance. This is a conditional covariance given x, and because x is random variable, we take expectation with respect to this target distribution. And because this is a covariance minus covariance, which is a concave minus concave, now this objective function is not concave in general. So once you have a hidden unit, nothing is really concave. But people still use a gradient-based method to obtain a locally optimal solution. So this is to summarize what we have seen when we have hidden units. So again, I use this notation S, which is a new notation U, and U can be a visible value or hidden units, a hidden value, depending on the index I. And S is all monomial of degree 1 and 2 for these variables. And we need to make sure that the order matches with this parameter theta. But if we be careful about this ordering, then we can represent the gradient in this nice concise expression, and the Laplacian with this concise expression. Okay, so far I haven't talked about how we actually evaluate expectation with respect to a moderate distribution like this. So it turns out to be I think I'm going to go to this expectation. Okay. Sorry, so we haven't talked about this discriminative learning. So let's briefly talk about this discriminative learning, where we want to learn the conditional distribution of output values given input values. So a natural expression, a natural objective function for discriminative learning is this. So we want to maximize the conditional log likelihood of data, which looks like this. So X is an input and output is an output. Y is an output. And we want to maximize the log likelihood of output given input over all data. And we also want to relate this to Kähler divergence. And here is how you can do it. So this is equivalent to maximizing the expected conditional log likelihood when with respect to the target distribution, when the target distribution is the empirical distribution defined by the data. So this is equivalent to this. And this can be expressed as, can be maximizing this is equal to minimizing this expression, which is the expected value of the conditional Kähler divergence to the target distribution. So this is a conditional distribution given the random visible values, and because this is this Kähler divergence is random variables, we take an expectation over this with respect to the target distribution. Okay, so in any case, our objective function is this. So this is to maximize the conditional log likelihood of data. So again. We just need to take the gradient with, of this objective function with respect to our parameter. And it turns out that you have already seen this gradient. So this objective function can be decomposed into two parts. So this is this one and this one. The first term is equivalent to the objective function of generative learning when the data is x and both x and y. So we want to so here we are maximizing this log likelihood of x for x and y. And this the second term is similar to the objective function of the generative learning when the data is just this input patterns. And in this case, we should think that output is also hidden. Output is hidden. And then we can apply the generative the gradient for the generative learning twice to get a learning rule for discriminative learning. And because of that, we get this simple expression that is similar to what we've seen in the generative learning, but it all looks like this. So again, the gradient has two parts, and this looks like this using our new notation S. And the Laplacian still has this expression as covariance minus covariance. So in general, it is still it is not a concave objective function. Yes. When to use generative learning and when to use generative learning and when to use discriminative learning. So I think it's if you want to learn the relation between input and output, then what you want to do is discriminative learning. So given input, what is the distribution of the output? That's what you want to do with discriminative learning. So generative learning is do not learn, just get input. So you want to learn the input distribution. And the purpose may be to generate a new pattern for following the data distribution. Okay, so far we haven't talked about how we actually evaluate the expectation with respect to model distribution. And these expectation appears everywhere in generative and discriminative learning of energy-based models. And this is actually the difficulty of this approach. So, for example, in the case of generative learning, when we have a hidden units, we have this expectation with respect to model distribution here and here. And for discriminative learning, we have here and here. And in general, this evaluation of this expectation turns out to be computationally intractable, and we need some kind of approximation, or we need to assume some structure in the model to allow to have some tractability. So I'm going to talk about several approaches to deal with this expectation. The first general approach, which has been quite popular, is Gibbs sampling. So the idea is to take some k samples from from the distribution that approximates the model distribution, and use these k samples to compute the sample expected values. So each iteration of Gibbs sampling goes like this. So we first initialize the value of all units. And in each iteration, we choose, for each unit, we choose a new value. And following the conditional distribution given by the previous values. So the previous value is fixed. Yeah. and repeat this for all units to get a new sample. And then this procedure is continued for k times to obtain k samples. So a problem of this Gibbs sampling is that it takes time to get a good for convergence. And there are a few other approaches. So one approach is just to change your objective function from k to divergence. So today I'm going to talk about two other objective functions. One is called contrastive divergence, and the other called score matching, and it is also called Fisher divergence in some papers. So the goal is to eliminate this intractable second term, which is a contrastive term. So I'm going to first talk about this contrastive divergence. So you might be more familiar with contrastive divergence as a learning algorithm, but here I'm going to talk about the contrastive divergence as an objective function. So to do that, so we first define the distribution of the samples that we get from Gibbs sampling. So the first step, we use the target distribution in Gibbs sampling. So the first, the distribution of the samples start from this target distribution, and in case iteration of Gibbs sampling has some distribution pk theta, and it eventually converges to your target distribution. So p theta infinity is also the same as, the target distribution here means that your model distribution. You're trying to sample from your model distribution. So eventually this distribution converges to your model distribution. So k divergence has this expression, and this second term is intractable even with Gibbs sampling, because this p theta infinity appears in this expression. So we need to run Gibbs sampling infinitely long to get an accurate estimate of this second term. So you want to remove this second term. So the new objective function is contrastive divergence, CD, and this is the k divergence from model distribution to the target distribution minus k divergence to the distribution of the first sample from the Gibbs sampler. So motivation of this contrastive divergence is this. So we want when when the model distribution is close to your target distribution, you expect that the Gibbs sampler don't change distribution over iterations. So your goal is to try to keep Gibbs sampler to stay at your target distribution. So you want a Gibbs sampler to stay at this, and you want to choose theta such that this property holds. So you run the Gibbs sampler one step and reduce the tendency of P1 first distribution to wandering away from the initial distribution. So this is the motivation of contrastive divergence. So it has some desirable property or some necessary property. So contrastive divergence is always non-negative, and contrastive divergence is equal to 0 if and only if your model distribution is equal to the target distribution. So it turns out that the exact contrastive divergence is still intractable. If you take the gradient, you still have this epsilon term, which depends on this p theta infinity. So you need to run Gibbs sampling infinitely. But it is empirically shown that this epsilon term is small. So what people use contrastive divergence is just to ignore this epsilon term. So Saki is going to talk a little bit more about the algorithmic aspect or some more advanced or some advanced topics of this contrastive divergence in part 2. So here is another interesting objective function called score matching or efficient divergence. So here our objective function is looks like this. So similar to Kerr divergence or contrastive divergence, it measures the distance from your model distribution to the target distribution, and this divergence has this expression. So it is expected value of this squared error with respect to the target distribution, and this error term is a difference between these two gradient. And what is important to note here that this gradient is not with respect to your parameters, but with respect to x, with respect to a pattern. So x needs to be continuous in this setting. But a very important property of this score matching is that this term is independent of the partition function. So your probability, so log probability has an exponential of negative energy divided by your partition function, but this partition function is independent of x. So if you take the derivative, you get this only from the numerator of your probability expression. So you don't need to compute a partition function, so it can be a very computationally efficient. But you might think that this is sort of intractable because you don't know the target distribution. You don't know the shape of the target distribution, and it is sort of intractable to estimate this gradient. But it turns out that there is a simple estimator which looks like this. It is independent of the target distribution, but it only depends on the gradient of the model distribution and the second derivative of your model distribution. And it can be shown that this score matching is a consistent estimator. So consistent estimator. So if you choose a theta that minimizes this score matching, this is a consistent estimator. And this quantity converges to score matching as we take more and more samples. It converges to this quantity almost surely. Okay, so far I talked about the approach of changing your objective function, but a recent approach, interesting approach is using a separate generator in an energy-based model. And this can be related to a generative adversarial networks, which has been popular recently. So if you look at the gradient of the log likelihood of the energy-based model, which look like this. So again, the first term is try to decrease the energy of sample from the target distribution, but this target is can be seen as your real samples. And this second term tries to increase the energy of samples that are generated by your model. So it can be seen as you're increasing the energy of your fake samples. And this objective is to better discriminate, to update your model parameters so that you can better discriminate between real and fake samples. So in energy-based models, this energy-based model acts both as a generator and a discriminator. But recent work on generative adversarial network says that we should separate generator and discriminator. So another motivation is that for this energy-based model, generator is sort of intractable. So some papers started using a simpler generator, which is easier to get samples from, and try to learn both generator and discriminator so that a generator can generate samples according to your target distributions. So there is also another related idea in deep reinforcement learning, briefly mentioned in part 4. So the last approach that I mentioned is called mean field Boltzmann machines, and it's going to be used in part 4 in the context of deep Boltzmann machines. But the idea is to choose to approximate this energy-based stochastic model with this simpler expression, where mi is associated with each unit and represents the probability that each unit takes the value 1. And this this m is chosen such that qm best approximate p theta. So, for example, by minimizing the k divergence between the two distributions. Right. So for the last part of this part 1, I want to talk about other energy-based models other than just Boltzmann machines. So, and these are the examples that I'm going to cover in the last part, in the last sections. So again, so energy-based. So first example is energy-based model, which is not associated with probability distribution. So purely uses energy to do inference and learning. So the inference goes like this. So here we are thinking about some discriminative learning. So given your input x, you want to give a best output y. So the idea is so the inference can be done like this. So you want to choose output y, which minimizes this energy function for a given input x. So and the learning part is more important. And so in the case of a stochastic energy model, this is your objective function. So you want to minimize the energy of some patterns that appear in your data, but you also want to maximize the energy of all other patterns. But this part is sort of intractable. So we want to replace this term with some tractable terms. So one example is for has been studied for phase detection, including pulse estimation, where you are looking at. So here they use this energy, which takes 3 input. The first argument is 0, 1, which represent whether the image is phase or non-phase. And second one, Z represents the orientation of your face, the angles, and X is your image, some like image. So given an image X, you want to say that if the image is phase or non-phase, and we say that the image X is phase, which is 1, if this quantity, which is the energy with phase level, is smaller than the energy with non-phase level, like this. And for tractable learning, they consider this objective function. So the first objective function is sort of obvious things to do. So we want to minimize the energy of the image X when it is labeled as phase. The second term is contrastive term, which is to increase the energy of a non-phase image when it is labeled as phase. So more specific energy function, more specifically energy function looks like this. So it is energy has three values. So X is your image, and X is input into this convolution network. And this CNN, the parameter of CNN is called W here, but it is for theta in our case. So G theta X is an output of your CNN. F is just a given function that maps this orientation into the same space as the output of the CNN. And you want to minimize the distance between these two output. And T is just a threshold when it is classified as non. So T is just an energy when the image is classified as non-phase. Okay, so for details, you can look at this paper. So and I just said that I just mentioned these name, class, and year. But if you look at the associated technical report, you can easily find the exact reference for all of these papers. Okay, so I'm gonna just for the rest of the talk, I'm going to talk a little bit about variants of Boltzmann machine or extensions and some related models. So, one model that we see in part next part, part 3 and part 4 is this thing. So we use expected values to represent the real values in hidden units. So instead of taking the marginalization of hidden values, which is often intractable, some paper uses expected values for hidden units. So hidden units is sort of like a deterministic unit and takes some real values between 0 and 1 instead of binary values. So we can define this conditional expected value of conditional expectation of hidden values given visible values, and it can be represented like this when it has a restricted Boltzmann machine structure. So hidden units, in between hidden units, we have no connections. So if this structure is holds, we can simply write the expected value of hidden given the visible values, which looks like this. So instead of a free energy we have seen it before, we can talk about the expected energy. This is again a function of x, but we take expectation with respect expectation for hidden values. So it looks like this. So Bx is this expression. So then the probability marginalized probability of visible values, there is no marginalization, but the probability of visible values has this expression. So there is an interesting relation between this expected energy and free energy. So expected energy is equal to free energy plus this entropy of the conditional distribution of hidden values. So if you plot it, we see that when H is close, hidden value is close to a deterministic, free energy and expected energy is essentially the same thing. But as we have more randomness in hidden values, there are some differences in these two quantities. So I just quickly go through other related models just for completeness. So Markov random field is just a natural generalization of Boltzmann machine, and so in this case, so energy has this more general expression of a linear combination of the feature of input patterns, and input pattern can take values from finite set instead of just binary values. So a particularly interesting case that appears later in this talk is a higher order Boltzmann machines. So in the case of a Boltzmann machine, this EX was a monomial of degree up to 2, but for higher order Boltzmann machines, this can be has monomial of higher degrees. So we're going to see some examples later in part 3. So we can also talk about some distribution energy model that gives distribution of real values. So one example is Gaussian-Bernoulli RBM. So if we consider energy, which looks like this, and let x2 take real values and h be binary values, we can see that a conditional distribution of x given h has a Gaussian distribution, and the conditional distribution of h given x has a Bernoulli distribution. We're gonna see this example again in part 2. So I think I'm okay. So let's talk a little bit about this spike and slab RBM. So this is an extension of Gaussian Bernoulli RBM. So it includes it adds this slab variable which takes real values. So h and s are both hidden values, but h is still binary values, and s takes real values. And there are a three-way interaction between x, h, and x with this particular form. So it turns out that this spike introduction of this slab variables improved this some capability of that capability that this Boltzmann machine can represent the distributions. And for example, it can be applied to generating learning generative model of images. And for example, these are the samples that are extended that are sampled from spike and slab RBM. In the paper, it is shown that it is sharper images than just using Gaussian Bernoulli RBM. I don't think I have much time to talk about this determinant point process, but this is not discussed, usually studied in the context of energy-based model, but it is an interesting point process which can be associated, which can be compared against Boltzmann machines. So if you define an energy like, as a log determinant of Lx, where Lx is a principal submatrix of kernel matrix X, L, where this principal matrix is indexed by X, this X. So when Xi is 1, we include this row and columns into this submatrix. And probably the distribution is defined like this. And it turns out that you don't have the intractable partition function in this case. The partition function turns out to be a determinant of this kernel matrix plus identity matrix. And there are several learning algorithms that have been proposed recently in machine learning conferences. So I'm gonna skip this one. And let's just summarize part 1. So we have seen that the contrastive terms appear naturally in learning energy-based stochastic models. And this term is needed for convergence, but it turns out that this is often intractable. Evaluation of this contrastive term is often intractable. So there have been some several approaches that have been proposed to approximate this second term, or to use a different objective function like contrastive divergence or score matching. And there is also a recent work on generative adversarial nets, energy-based GAN. So we have seen one advantage of energy-based model that it is easy to design an energy so that you have more tractability, which we're going to see in the next part. But it also easy to incorporate your prior knowledge in the form of the structure of the energy. We're going to see more examples in part 3. So we're going to also so in part 4 we're going to see also use energy in completely different purposes, which is to approximate a function in reinforcement learning. So that's it for part one. So if you have any questions from part one, please raise your hand. Otherwise, yes.
Set it up, you can take some questions. You want your... Okay, so this part is going to be largely a historical perspective, covering basically energy-based models that we have seen, and variants of it, like restricted Boltzmann machines and deep extensions of those, wherein previously this basic energy-based model was largely intractable. So previously we looked at the Boltzmann machine, which looks like this, wherein you had connections. So the simplest Boltzmann machine would have this form. So you have some form of visible connections, so visible units, and you have some hidden units. But there is connection or interdependence between the visible units as well as the hidden units. As a result, you have these quadratic terms in your energy function, which made learning these models quite difficult, as a result of which we would have to use some form of approximation methods. So what restricted Boltzmann machine did is that it introduced an undirected graphical model, which now has, again, two layers of visible and hidden, with the main distinction that there are no more connections between the visible to visible or hidden to hidden units. So essentially no connections intra-layer. And that simple formulation of a bipartite graph structure with no intra-layer connections removes those the dependent terms of x and h and h from the energy function, which we'll see helps us to learn these models much more better. So it makes the data dependent expectation that we have seen previously more tractable. And for the model dependent expectation, we will still have to use some form of approximation, and we'll see what that is. Okay. And it also turns out that from the early works, it has been shown that these restricted Boltzmann machine are essentially universal approximators. So if you add a single hidden unit, you essentially guarantee increasing the log likelihood of your data. And that essentially enables you to learn a generative model of any form of data distribution. So if you have enough hidden units, you could perfectly model any general discrete distribution. So we will not go into the details of the derivations of this, but of course you can refer to the a paper from Lerox and Bengio from 2008. So what was the benefit of removing these connections between the visible to visible or hidden to hidden units? Essentially, it makes the conditional distributions quite nice. So now what we have is that the conditional distribution can be written in the form of these product distributions, essentially because you have no more dependence between those variables. And this makes the inference of these models quite efficient. So now we can do Gibbs sampling more easily. Particularly, we can apply block Gibbs sampling on the entire layer. So you could apply Gibbs sampling to all the hidden units or all the visible units, which makes the sampling procedure much more tractable. And we can also show that typically, like the standard Boltzmann machine, the restricted Boltzmann machine was also classically defined for Bernoulli or binary variables. So basically variables that take zeros and ones. In that case, for Bernoulli variables, the probability of your visible unit taking a value 1 given your hiddens can be represented using a sigmoidal. So basically takes the sigmoidal form, and the same thing for your hidden given your visible. And this allows us to have an interpretation of this kind of a Boltzmann machine to give you some form of feature representation of your data distribution, as we'll see later on. So essentially you have a sigmoidal or nonlinear transformation function. So in the first part, we also looked at free energy. Typically, in case of the RBM, you can also define the free energy, which gives you a nice form of your marginal distribution P of x. So typically in these energy-based models, what we want to learn is this marginal distribution. So the likelihood of, so learn to model the data distribution itself. So P of X essentially is equal to marginalizing over all the hidden units, which in this case, if it's binary, then over all of them take values 0s and 1 of the total joint distribution over the visibles and your hiddens. If you write out the joint distribution in the form of the energy function, it's essentially equal to the exponential of your energy function normalized by the partition function z. And z, of course, in this case, because you have hidden and visible, you need to sum over all the visible and hidden units. But now if you introduce the formulation of your energy function inside, so here basically this is nothing but the energy function of your restricted Boltzmann machine. So C here represents the bias terms, so the bias associated with your visible units, and B would represent the bias associated with your hidden variables. And this term, as you see, is quite nice. So because it now is a linear sum over all the, so M represents the total number of hidden. So you are linearly summing over all the hidden units. And this term is basically what is referred to as the negative free energy. So f of x is basically this negative of this term. And this once again gives you a nice formulation that we are familiar with from before. So not only the joint distribution, but also the marginal distribution now can be represented in the form of exponential of some energy, which in this case is free energy, normalized by now the same partition function. And this free energy term allows us to once again kind of see that this free energy represents a nonlinear transformation of your data. So this is similar to a softmax function as depicted here. So essentially, once again, this represents some form of feature transformation of your data that you're trying to learn with the model. Okay. So of course, the main idea of these models is we want to learn the parameters of these models such that we can represent the data distribution better. So as we saw in the first part, one way to do this is basically to use a gradient descent approach, or what we'll call essentially a maximum likelihood estimator. And in order to do that, we want to find out the parameters with respect to, so we'll use the objective function, which is the log likelihood of your data. So the probability function once again can be represented in this form. Now, in case of RBM, you can replace this energy of x by the free energy as we have seen. So the free energy would have the same formulation. The partition function once again sums over all the variables in the model. So if you have both visible and hidden units, here x represents both the visibles and the hidden. So you have to marginalize over all of them. What we want to do is differentiate, basically find out the gradient of this log likelihood with respect to the parameters of the model, which gives you these two parts. The first part here is tractable again, because this, in case of the RBM, can be written in the form of the conditional distributions, which is quite nice for us. However, this partition function, which requires us to sum over or marginalize over all the visibles and the hidden, is still untractable. And in order to learn that, we'll see that we'll use some form of approximation method, essentially contrastive divergence and variations of that in order to learn that model. Okay, so that's basically what is represented here. Okay, so how do we actually go about training such a model? So what we want to do is learn the parameters of this model. So let's consider that given some IID samples, x1 to xt, so these are the different samples of your data that you essentially want to model. From the marginal distribution P of x, we want to learn this RBM using a maximum likelihood estimator. So this P of x again can be written out in the form of the energy function. The objective function that we'll use is essentially the log likelihood of your data, parameterized by the model parameters, which in this case could be the bias and the weights. So C and B are the bias associated with your visible and hiddens, and W is the weights between your visible to hidden units. So what we want to do, once again, like we saw in the previous slide, is we want to find out the gradient of this log likelihood with respect to the parameters of the model, which is the bias and the weights. So if we consider a single sample likelihood given by, say, x of t, which can be written out in this form again. So this is nothing new. It's the same formulation. If we differentiate this with respect to the parameters, say the bias b of I, it gives you again a very nice formulation of two different expectations. The first expectation consists of, so it's expectation over the conditional distribution p of h hidden given your sample x of t. And the second one is your expectation over the joint distribution x and h, which comes from this partition function term. Once again, this is untractable. The same thing, the similar formulation will occur for all the other parameters. What we are primarily interested in is this term. So the weights between are visible to hidden units. So there are two different typical terms. So we have seen this in the first part. So Osogami basically called this the target dependent term. So that is basically what I'm calling the data dependent term. So this is again tractable. Whereas the second term is model dependent. So this is coming from a model, and this again is untractable, and we'll see how to kind of approximate this expectation. Okay. So once again, the way to do this, as was introduced in the first part, so you could essentially use a Monte Carlo sampling procedure or a Gibbs sampling procedure to approximate this second expectation term, so the expectation of your model dependent terms. However, if you just do simple MCMC sampling, typically that would be very slow, as we saw. So you need to sample over an infinite MCMC chain in order for that to converge to the two data distribution, which is typically not feasible. So Hinton in 2002 introduced this formulation that was also kind of talked about briefly in the first part, called contrastive divergence. So this contrastive term comes from this expectation. So the idea out here is that now once again you are going to do use a MCMC chain. So you basically, this is a normal MCMC chain, but you're going to initialize this MCMC chain from the actual sample of the training data. So at t is equal to 0, so typically you want to run this for infinite chain, but at t is equal to 0, you initialize this from the sample of your the true data that you have, the training data that you have. Once you do this, because in the RBM there are no connections between the hidden to hidden or the visible to visible, we can use block sampling and get the probability of your hidden given the x's for all these units. So probability of this jth unit equals to 1 given x, and so on and so forth. Once you do that, in the next step, basically from this you can get the probability distribution of your visible given this hidden of this of your model. And then if you repeat this for k steps, you get basically what is typically called a fantasy particle or a negative sample from your model distribution. So this is basically your model's representation of your data. And typically for contrastive divergence, it is sufficient to run this chain for k is equal to 1 step. So just one step gives you typically good samples. However, in practice, you would run multiple such chains in parallel. So you would run, not just a single MCMC chain, but you would typically run many such MCMC chains in parallel, and you can also use different k values. So you can start with, say, CD1, you can also do CD2, CD3, CD10 in parallel, and that gives you a better estimate. Okay. Okay. So once again, so this is another intuitive way or a pictorial way of understanding what is going on with this contrastive divergence procedure. So what we expect is, let's go back again. So what we expect is we want to make these negative samples. So we want to learn a generative model of our data. So ideally at the end, when the MCFC chain has converged, what we want that whatever we sample from the model, it should look as similar to the data as possible. And so the idea is that given this energy function, so a minimum energy is essentially associated with a higher probability. So in the beginning, this xi is basically what is coming from the data samples, so the true target data that we have, and x tilde is basically your fantasy particle or the negative sample, and you would typically have a lower energy associated with it, which is basically bad. And this contrastive divergence procedure is changing this, so it's essentially lowering the energy associated with the true data, and or in other words, increasing the probability of your model giving you samples from the true data distribution and making the probability of these fantasy particle to be some random sample as low as possible. So, or in other words, increase the energy associated with this random fantasy particle as much as possible. Okay. So by repeating this process, this essentially allows you to learn a generative model of your data. However, the classical contrastive divergence can still be quite slow. So if every time you initialize, so let's just go back once again. So if every time you start this CD chain or your MCFC chain, if you initialize with the training data, it's essentially wasted, because you could, so every time you run the CD chain, you come to some fantasy particle. So now when you're reinitializing to x of t, you're essentially throwing this away. So there is no kind of persistence of your Markov chain that you had got. So one simple idea is essentially to use a persistent Markov chain. And in this case, what you do is that you jointly update the negative samples, so of both your so your hidden and your visibles, and the network parameters by repeating the following two steps. So essentially you fix the parameters of your model, so which in this case would be, say, the bias and the weights, and then you sample the next negative sample or fantasy particle. Once you do that, then you update the parameters with respect to the gradient. So this is again nothing but the gradient that we have seen previously, wherein this expectation is replaced by this point estimate that is coming from your Markov chain. So this is being replaced by this estimate. And this is essentially the idea behind persistent contrastive divergence, which was introduced by Tillman in 2008, wherein you're preserving the state of the chain for every subsequent states. So previously here, instead of x tilde, you were using x of t. So every time you're reinitializing to from your actual data sample, but instead of doing that, you can use the same fantasy sample that you had got from the previous iteration itself, which essentially allows you to preserve the state and makes the CD algorithm much more faster. So that's the main idea. Okay. So once again, the K typically can be one step, but in practice, you would run many different Ks in parallel. So you will typically not run a single MCMC chain, but many multiple parallel MCMC chain initialized with different K steps. And then that allows you to get a much more better approximation of your data distribution. Okay, any questions so far? Okay, so pretty simple. So of course the original RBM was, again, as I said, was similar to the Boltzmann machine, was defined for binary or Bernoulli variables, which take values from zeros and one. But most of the data that we are interested in the real world, for example, images or text data, are not binary, so they are real value data. So a simple extension, as was also kind of introduced in the first part, is to use a Gaussian representation of your visible units, and that's basically what is called a Gaussian Bernoulli RBM. So in this case, the x's, so x here again represents the visible units, can take unbounded real values, but your hidden units are still Bernoulli, so they are still binary variables which take values zeros and one. The difference being that now you just have an additional quadratic term introduced in your energy function, and the conditional distribution of your visible given the hidden is considered to be a Gaussian distribution with a mean which is essentially equal to the bias associated with your visible unit C plus the product of your weights between visible to hidden and the activation of hidden nodes. Typically, you could choose an identity covariance matrix, or you could also learn or parameterize the variance itself. In practice, if you have also a parameterized variance, it's difficult to learn. So it is observed that using an identity covariance matrix gives you sufficient performance with a Gaussian Bernoulli RBM. However, unlike the classical restricted Boltzmann machine, which is the Bernoulli variable case, the Gaussian Bernoulli RBM is still pretty tricky to train in practice. And that's one of the reasons why it hasn't been used as much as its classical variant, though it gave some really good performances. So two typical tricks that is used in practice is that you normalize your training set. So this kind of lets this Gaussian distribution handle that data well. And the second thing that you do is that you typically use a much more slower learning rate as compared to what you would have used with the classical restricted Boltzmann machine, which allows your learning to be more stable. So no real theoretical background behind this, mostly heuristic formulations to make your learning much more better. Both of these tricks have been extensively tried out in many different papers, notably from Chris Wesky in 2009. Okay. So once again, so many of this work, by the way, has occurred in Salakudnov and his talks. And so many of the things will be familiar with those things presented by him previously, as well as majority of the work done in this area has been from Salakudnov and collaborators. Okay. So RBMs for real value data. So essentially now that we have a Gaussian Bernoulli formulation wherein the hiddens are once again values which take values between 0 and 1, but your the visible units now take real values, you can actually learn the data distribution corresponding to real image data, wherein the real images take real values. So you could train this RBM on unlabeled images. So essentially what you want to do is learn a generative model of these images, and just using a simple RBM with one hidden layer and a visible layer gives you somewhat similar to Gabor-like filters. So it's not really Gabor-like, but you get some form of feature representation of your image data. And by summing them correctly, so having a weighted summation of these, essentially of your, being able to sum these features together lets you generate new images that you from the unlabeled image data that you've trained your RBM model on. Okay. All right. So once again, to recollect, so as we have seen that this free energy or the representation of the sigmoidal function in our RBM essentially acts like is essentially a nonlinear feature transformation of our data. So we don't have to restrict ourselves to a single layer of an RBM. So if we essentially stack up this RBM one after the other, we could learn some form of higher level representation of our actual data. And that's the main idea behind, or one of the major initial motivations of using deep learning. And this model was known as a deep belief network, and we'll see what the model exactly looks like. But the intuitive understanding is that you progressively learn higher level features of your data, wherein this one is basically the hidden layer of your first level RBM, which acts as the visible layer for your second level RBM, and so on and so forth, giving you a much better representation of your data. And you could essentially do this for n number of such layers, getting progressively better representation. Okay. So what a deep belief network is essentially now it's a combination of both a undirected graphical model, which we have seen previously, so which was familiar in the Boltzmann machine case or restricted Boltzmann machine case, but now it also has a directed part, which is basically a directed sigmoid belief network. So the highest level essentially is an RBM, whereas the lower layers are a directed graphical model, and this directed graphical model once again has a nice formulation because you can now represent the conditional distribution of your H1 given H2 or visible given H1 in the form of the product distributions. So in individual conditional distributions. And once again, the reason being, you do not have any connections between your visible to visible or hidden to hidden. So we still maintain the same form of bipartite structure with no intra-layer connections, which allows us to have a much more tractable conditional distribution. So the total joint, so the entire joint distribution with respect to your visibles and hiddens can be written in the form of the products, wherein this joint distribution of H2 and H3 is nothing but what we have seen already, given by a restricted Boltzmann machine. And these are once again sigmoids. Okay. And for simplicity, we are basically ignoring all bias terms out here. So the weights W1, W2, W3 are essentially the parameters that we are going to learn for this model. But it's quite non-trivial if you want to introduce bias terms as well. So this EXP would then have bias. So exponential of your this term would then have the bias terms as well. Okay. So with this deep belief network, essentially Hinton and collaborators introduced a formulation of greedy layer-wise pre-training that we'll see. Essentially the idea being that you can train this model layer by layer, so one RBM at a time. And that allows quite a nice approximate inference as well as a generative process, wherein, so Q represents the probability, the conditional probability distribution of your H1 given the visible. Once you have that, this hidden unit acts as the visible units for this layer of RBM, and you can get the probability distribution of H2 given H1 and so on and so forth. And for the generative process, once you have the joint distribution, so this joint distribution once again can be learned using what we have seen, the contrastive divergence or persistent contrastive divergence. So here you would have again a data dependent expectation and a model dependent expectation. The data dependent expectation once again is tractable because there are no connections, but the model dependent expectation can be learned using contrastive divergence based Gibbs sampling. And then this part, because of its directed flow, essentially gives us these conditional distributions in terms of the products that we have seen out here. So these are quite simple. So as I mentioned, so the main idea here was this greedy layer-wise pre-training, which essentially laid the foundation for most of the work that has been done on deep networks. Although these models have now kind of lost, it's not so much used anymore as such. So deep belief networks, though introduced kind of a nice formulation, they were not as powerful as the other deterministic variants as well as kind of stacked autoencoders. However, nevertheless, this formulation has still remains. So even with autoencoder type networks, you follow a similar formulation of layer-wise training. So idea being, as I mentioned, you start by learning an RBM with an input layer V and hidden H. So here your V is once again your visible or your data. You're learning this as a simple RBM network. Once you do that, you treat this inferred values as the data for the second layer RBM, and then you freeze the weights. This allows you to essentially do layer by layer training of this kind of a stacked RBM model. By the way, there are some theoretical proofs that can show that such layer-wise pre-training improves the variational lower bound, which is also quite nice. You can not only use these models for kind of generative learning, but you can also do classification or supervised learning with these kind of a deep belief network. So a simple thing would be if you have access to labeled information, so some labeled data, so you can train a joint generative model by maximizing the entire joint log likelihood of your data and the labels. So here your Y are the labels associated with your visible. Okay. You also another, so one of the major uses of these deep belief networks were not in form of actually learning the data, but using as a pre-training procedure for initializing some multi-layer neural network. So you could use this DBM to initialize a similar structured multi-layered network, and you get an initialization of your weights. So instead of starting a training of a multi-layered neural network with completely random weights, you essentially use the weights that was gained by such a pre-training procedure. Okay. So as I mentioned again, so we have already seen this. So the joint distribution over your visible and hiddens is given by these products. Whereas this is quite simple because these can be represented in form of the product of their individual conditional distributions. And this one can be again approximated using the sampling procedure as we have seen. So the topmost layer being an undirected graphical model or a restricted Boltzmann machine can be estimated. So you get your H2, so which is basically in this case similar to visible nodes as we have seen previously, can be got by using a conditional contrastive divergence procedure or a Gibbs sampling procedure. And then you essentially propagate this information downwards till you get the probability distribution of your visible given the hidden from the previous layer. And this part is from your directed graphical model, so sigmoid networks. Okay. So these models were used for classification purposes and gave quite good results on historic data sets like MNIST. So MNIST is basically a pretty simple data set to work with. However, these models give quite significant results, which basically worked much better compared to the previous state of the arts like SVMs. That was the norm, or simple multi-layer perceptrons. Once again, the pre-training procedure would be as we have seen, so a greedy layer-wise pre-training. So you start with your data, which is, say in this case, your MNIST data, and then you learn one layer of RBM, then you learn a second layer of RBM, and so on and so forth. What you could also do is that you could unroll this entire stacked set of RBMs, and then finally learn some kind of a mode or classification units. So these basically give you a softmax output given what you have learned in the previous layers, with which you can essentially learn to classify these images into their corresponding labels. So 2 is 2 or 3 is 3, so on and so forth. What you can also do is that if you have access to the true labels, you can essentially use an error between your classification from the model as a distance from your true labels, and fine tune this using backpropagation of the error through the layers. And that makes the model even better. So you could not only learn a generative, so you can learn the parameters using the procedure we have seen, but you can also fine tune that procedure using backpropagation of error through the layers. You can also use these models, or it has been shown to be used as a deep autoencoder. So essentially, in the previous case, what you're learning is an encoder step, but you could also unroll them, and then from this kind of a code layer, which previously was the softmax layer that we have seen, you could also do the inverse procedure. So given those, you can go back and learn to generate the data itself, so decoder step. And once you have that, if you fine tune this network, so use the error to backpropagate the error through the layers and fine tune the weights, the samples generated by this autoencoder network is pretty much as good as the true samples. And this has been used for example, this kind of facial recognition and many applications over the years in literature. This 2006 is pretty old now. Okay. All right. So not only with image data, but this kind of models have been used in information retrieval. So for example, we have seen, so I will not go into the details of this. However, so previously we used this Gaussian-Bernoulli model to deal with essentially real valued visible units, but you could also have a softmax type visible nodes. So that would be a softmax Bernoulli RBM essentially. So once again, your hidden units are still Bernoulli variables, but your visible units take a softmax, kind of a softmax function, and which has shown to work pretty well as compared to a lot of the state of the art that existed at that time, which is essentially topic models. Okay, so that brings us to another form of a deep stacked restricted Boltzmann machine. So previously, when we had stacked this restricted Boltzmann machine, we basically assumed that there is it's a mixture of undirected and a directed graphical model. But you could also have a completely undirected graphical model. So in this case, you once again have stacks of restricted Boltzmann machine, but there is no directionality. This makes things interesting as well as difficult. So as compared to your deep belief networks, inference in DBNs, there was one. So essentially, because of the directionalities, you get into these explaining away problems. Also, this greedy pre-training procedure did not allow you to essentially have a joint optimization over all the layers. So you would have to do this one by one. And the approximate inference, as we saw, was essentially feed-forward. So you did not have bottom-up and top-down inference. So basically, for example, this node has dependence in this direction. Whereas in case of deep Boltzmann machine, if you take one of these nodes, it now depends on both these hidden units as well as these units. So that makes the model more powerful, of course, because now you can learn you can jointly optimize across all the layers. But we will see that it makes the learning procedure difficult because now both the expectations, that is your data dependent expectation as well as the model dependent expectation, both become intractable because now you have dependence across the layers. So once again, you can write out the marginal distribution. So by the way, sorry for the mix-up of the notations. If you have not realized by now, V is what I was representing as X previously. So the visible units are now called V, but previously we were calling it X. Essentially, it's the same. So that's a small change in notation. So now, so your marginal distribution given the parameters of the model, which is theta, can again be written out in this form, wherein you're summing over all the hiddens. In this case, H1, H2, H3 for a 3-layered DBM. If you have more layers, you would have correspondingly n number of such hiddens. And this again is nothing but the energy function. Once again, we are neglecting bias parameters for simplicity, but it would be quite non-trivial, quite trivial to introduce bias terms in your energy function out here. Okay. So as we see, so here, as I mentioned, so because you have dependence now between these hidden units as well as these hidden units. So if you try to find out what is the conditional distribution of the hidden unit in the second layer, given H1 and H3, you would have two different influences. One being the bottom-up influence coming from here, so summing over the product of these weights corresponding to all these hidden units. And the second term would come from the dependence of, so the product of the weights associated with all these hidden units. And that typically makes this learning procedure difficult. So whereas this conditional distribution is no longer tractable for us when we do the learning procedure. Okay. So similar to as we have done till now, we want to essentially learn the model parameters using a maximum likelihood learning. And as we know, if we use once again the log likelihood of the so differentiate find out the gradient of this the marginal distribution with respect to the parameters. Say for example, I'm representing with parameter W1, but you would do the same thing for all the different parameters. You once again get a nice formulation of two different expectation. The first one being the familiar case of data dependent expectation, and the second one coming from the model itself. So here this is dependent on the model parameters. Unlike in case of RBM as well as deep belief networks, this expectation is no longer tractable anymore. So now in order to learn this, we need to approximate both of them. So we need to find some form of method to be able to approximate this expectation as well as this expectation term. The second one can be done using a familiar thing. So as we have done previously using contrastive divergence or essentially Gibbs sampling. So you could use stochastic approximation and replace this expectation by a point estimate and get this model dependent expectation. But what do we do about this data dependent part? So in order to do this, we will essentially use a variational inference procedure, which was somewhat talked about in the first part using this mean field approximation. So let's see that. So in order to do this approximate learning, we are basically going to assume that this conditional distribution, which is no longer tractable, we are going to assume that we have access to some simpler tractable distribution given by Q, parameterized by mu. So this Q essentially represents some naive mean field tractable distribution for which we are basically going to make sure goes as close as possible towards this intractable distribution that we want to access. So if you write out the log of this marginal distribution, essentially it can be written as the sum over your hiddens, which has a nice form. So now if essentially what you're doing is you're introducing one term. So this divided by this is essentially 1, but that gives you a nice formulation or representing this in the form of a lower bound, wherein you get, so this term is essentially equivalent to a KL, so this whole term is equivalent to sum of the log of the marginal distribution minus the KL divergence term. So this KL divergence term comes quite straightforwardly if you replace this P of, so this joint distribution by the conditional distribution. So you, instead of P of theta of H comma V, you can write this out in the form of the product of the conditional distribution and the marginal distribution. And what we want to do is minimize the scale divergence between this approximate distribution that we still don't know what it is, but we're going to find some nice representation of this marginal distribution. And we're going to minimize the scale divergence between this approximate distribution and our intractable posterior distribution with respect to some variational parameters mu. And this mu is basically what defines our so-called tractable distribution. So by the way, this lower bound has an exact solution, of course, only in one case where these two distributions are exactly equal. Okay. So as we had seen in the first part as well, so you could now represent this, you could have a naive mean field approach where you choose a factorized approximating function. So you choose this approximate conditional distribution as a product of these conditionals, where the probability of h of j being equal to 1 given v is equal to this the corresponding mu parameter. And what this variational inference procedure is going to do is that for each of the training sample, we're going to find those values of these variational parameters mu that maximize this lower bound that we have seen previously for the current value of a model parameters theta. So essentially what it means is that while we're doing this variational inference procedure, we assume that the model parameters are fixed. So the model parameters are not changing, right? So given for certain model parameters theta, we want to make sure that our mu allows us to get a approximate estimate of this conditional distribution. And you can also get the optimum. So this optimum should satisfy these mean field fixed points, which can be figured out in this form. So here, once again, we are only considering, so there are no bias terms, but again, it is quite trivial to introduce bias terms within these mean field fixed points. Okay. So once you do that, so if you, now that we have been able to essentially use this kind of a variation inference procedure, we can get an estimate of this conditional distribution. So now we have approximately moved towards the actual conditional distribution that we want to find. If we are able to estimate that, we are able to estimate this expectation. So now we can approximate this data dependent expectation using this variational inference term. But we still have this model dependent expectation. And for that, we are going to do a stochastic approximation, or the familiar case that we have seen previously of using MCMC sampling to get that expectation term. And for this, similar to what we have done in case of the RBM or was talked about in the first part, we are basically going to update your model parameters theta sequentially by replacing this intractable term. So this expectation which is intractable, once again we are going to replace that by the point estimate that comes from your MCMC sample. So once again you run many such chains of your MCMC chains, and for example for k steps, and for each of those MCMC chains you replace the intractable expectation by the point estimate. And if you do this procedure for enough number of steps, we know that the estimate of the model distribution is going to go as close as possible to the true target distribution or the data distribution. Once again, in practice, instead of running a single Markov chain, you would want to run several such chains in parallel, which essentially allows you to do this approximation procedure much more better. Also, as we had seen in case of the using persistent Markov chain, in case of the RBMs, you can again use the same procedure. So at every point in time, you can keep a persistent state of the Markov chain. Okay. So finally, let's just essentially see a simple application. So there are many such applications of this model. But one of the notable applications which I find quite interesting is basically to learn a multimodal distribution. So basically being able to move between modalities of data. So because now with these deep Boltzmann machines, you can do both top-down and bottom-up inferencing, and you can jointly optimize across all the layers. You can learn a model which looks like this, wherein you can have one set of visible layers which basically have are the visible data of your images. So this one essentially represents the visible images, visible nodes using a Gaussian Bernoulli representation. And you can also have another set of stacked RBMs or deep Boltzmann machine, wherein this its visible units have a softmax representation. So this one is a softmax Bernoulli RBM essentially. But then you can have a shared hidden space. So because the hidden space is still Bernoulli variables, zeros and ones, so you can have a shared representation across both of these models, which allows you to essentially infer from, so given this is fixed, so given the images are fixed, you're able to generate visible or data distribution which basically is dependent on these visible units and vice versa, which was applied quite nicely in these works. So this is one of the earliest work, by the way. So the original paper was in 2012 NIPS. So this one is a subsequent, I think, a journal paper in JMLR. But there have been many other works which have essentially used similar ideas to generate multimodal distributions, multimodal data distributions. So here, as you see that given your images are fixed, so for a butterfly, you get quite nice generated data. So it's called an insect, butterfly, bug, so on and so forth, which seems quite realistic, or what a human would also call. But sometimes the model, of course, fails. Like in this case, perhaps the sky does look like bubbles, but anyhow, this model fails in certain cases. This was trained on 1 million data from a Flickr data set. So still, this was one of the earliest examples where such a multimodality could be achieved using a deep Boltzmann machine. However, you would have probably realized by now, because you have to do this kind of variational inference procedure as well as stochastic approximation procedure, which involves joint approximation across all the layers, training these deep Boltzmann machine is significantly slower. So typically 2 times slower as compared to what you would have done with a deep belief network. Okay. So to summarize this part of a historical perspective, what we have essentially covered is we have seen you can have, so by removing these intra-layer connections between visible to visible and hidden to hidden, these restricted Boltzmann machines act as universal approximator, wherein it also allows us to have a much more tractable handle over getting the data dependent expectations, as the conditional distributions are quite nice. We have seen that you don't have to be restricted to binary data. So you can have formulations of Gaussian Bernoulli or softmax Bernoulli types, which essentially allows you to deal with real valued, unbounded real value data. You can also stack these RBMs and use a layer-wise pre-training procedure, which essentially allows you to have much more stronger feature representation of your data distribution. And this kind of greedy pre-training procedure does not allow you a joint optimization across all the layers, but can be used as a pre-training step for essentially initializing multi-layered neural networks. So you use this kind of pre-training procedure and don't select your weights from completely randomness. Deep Boltzmann machine gives you a lot more power. So now you can jointly optimize across all the layers with both bottom-up and top-down inference. However, it gives you a caveat that now both your expectations are intractable. So both the data dependent and the model dependent parts become intractable, but you can solve that, as we have seen, using a combination of variational inference using naive mean field approaches, along with an approximate sampling procedure, which we are familiar with. So basically MCMC sampling. But as I said, this model, though very powerful, is significantly very slow as compared to the previous models. Okay. Are there any questions for this part? If not, we'll move to the third part of time series predictions.
Okay, so we have a break from 4, but until then, I want to talk about part 3. Okay, part 3 is on Boltzmann machines for time series modeling or learning. Okay. So again, this part, much of the derivations or references in this part is contained in this technical report, which I published this morning. So you can find the link from our tutorial webpage. So I'm going to start with some motivation about why we want to learn time series now. So time series is still an active area of research, which has been studied for a long period, but still an active area. In machine learning community, there has been some workshop and tutorial that has been held in KDD, NIPS, and ICML very recently. So one reason is time series data is ubiquitous, and the amount of such data is growing, and still it is quite difficult to deal with. So examples of time series can be seen in sensor data and financial market and climate and simulation, physical simulation, music, movie, and so on. So the goal of time series learning that's going to be covered in this tutorial is that we're going to learn a generative model of time series, and this objective is to maximize the log likelihood of given time series. So this log likelihood can be always decomposed into the product of a log likelihood of this conditional distribution, which is conditioned on all past patterns. So typically we study Boltzmann machines that can represent this kind of conditional distribution. So applications of this generative learning of a time series is in forecasting or anomaly detection from time series data, or it can also be used to generate new time series, such as music or the document and so on. So other related goals of time series learning, which is like classification, clustering, or change the point detection or structure learning from time series learning, you need to do a little bit more work, but the basis on this generative learning of the time series. So So I'm going to start with a Boltzmann machine that has no recurrent structure, but that can represent the time series models. So one standard approach or one standard model of this type is called conditional restricted Boltzmann machine. It is just a standard RBM, but it has an input part and output part. Input part is given, and it usually represents some past observed patterns. So this is the observed pattern at time t-1, and this is the observed pattern in the previous step, and so on. So what you want is to have a distribution, model a distribution of this output pattern, which is your next pattern, and this distribution should depend on this the previous patterns that we have observed. Well, except that this is used for time series modeling, nothing is really special about this conditional RBM. It is just a conditional restricted Boltzmann machine. But when you have D layers in this input layer, you can represent some these order Markov model. So it's good to see some examples of this application. This is applied to human motion modeling. So you can see that this represents, so the first node represents walking motion, and second one is running, and third one is start from walking and then to running. The first movie is trained with just walking pattern. So it when you after training, if you generate a new time series, you just see this walking patterns. The second part, second and third model is trained using both walking motions and running motions. But but the difference is that the second motion, when you generate the second motion, you are given an initial series of running patterns, and when you follow that, you get to see this running motions. But the third pattern that we have seen is start with this walking motion. But because the model is trained both with walking motion and running motion, somehow it's in the middle, you switch from walking motion to running motion. So it's been quite successful in learning this kind of a structured pattern, time series of structured patterns, such as human motions. So there has been some extensions of conditional RBM, which I don't talk so much about it. But so for example, we can have multiple or deep hidden layers that we have seen in the second part, like this. So we can also have this three-way interactions between input, output, and hidden. but this can increase the number of parameters significantly. So an interesting approach is to factor this three-way interactions in this way. So, and it also so this WIJK can be also depend on F, where F can, for example, in the case of human motion modeling, F can represent what motions that you are learning. So maybe it may be walking, running, or doing some other activities. One potential limitation of this kind of a non-recurrent Boltzmann machine for when it is used for time series modeling is that it can take into account only the dependency within a predetermined horizon. But you can always increase this horizon D, but as you increase this horizon, the computational complexity also increases. So this is the motivation for the next part of recurrent, the use of the recurrent structures. So I'm gonna for this part, I'm gonna start with some classical model of spiking Boltzmann machines and temporal RBM. But I think this is I think knowing these two models gives you some good motivation for more recent work on recurrent temporal RBM or dynamic Boltzmann machines. So I'm going to start with this very old model of spiking Boltzmann machine. So similar to a conditional RBM, it has this visible layer and hidden layer. But the visible layer has this infinite horizon, and the hidden layer also has this infinite horizon. And another difference is that these hidden values are sort of recurrent. So after you get, so this hidden, but the next hidden value is going to be used in the next step as the input values. But hidden values are random in Boltzmann machines. So so it is sort of intractable to do exact inference and learning with this model. So the approximation is that has been used in this Hinton's paper is that these are historical, for these historical hidden values, they use sample values. So at every step, you sample from the distribution of hidden values, and those sampled values are going to be used in the preceding succeeding steps as this input. There is also an assumption that the output is independent of future hidden values, but this is also similar to the directed model that we have seen in the previous part. Another assumption or some technique that is used in this paper is that because we have an infinite number of layers here, you can have infinitely many parameters, which is intractable to deal with. So they introduced this parametric form of the weight. So W tau is the weight from the values at time t minus tau to values at time t, and this is approximated with this R tau, which is a function which looks like this with this W. So this function is fixed, arbitrarily chosen and fixed, and the goal is just to learn this weight W. So with these approximations, this can be seen as just an energy model, but it has some weird strange characteristics. So this conditional energy now depends on your past sampled hidden values. So the energy function looks like this. And it turns out this is a restricted Boltzmann machine with time-varying bias, but this also depends on what you have sampled in the past for your hidden values. So your bias term is time-varying, but it also depends on what samples that you get for your hidden values. So it can be seen as some sort of approximations. So another issue or some property of this spiking Boltzmann machine is that we don't know what it is not learning. We don't know which hidden values are good for prediction until we observe future values. And for this reason, it is not learning what hidden values should be created to make future predictions better. But hidden values are useful in this case to model the dependency between these output values, but not helping the future predictions so much. Okay. So I think I want to also talk about temporal RBM and hopefully recurrent temporal RBM before the break. So this is also similar to conditional RBM, but with similar recurrent structure to spiking Boltzmann machines. But instead of using sampled values, they use these expected values for these past hidden values. So the distribution of the next visible value and hidden values, it depends on your previously observed visible values, as well as these expected values that has been computed. Again, it is a sort of a kind of approximations. But what is a significance of this temporal RBM? That it naturally motivates this next model, which is called recurrent temporal RBM. So recurrent temporal RBM has this structure. So again, so this part, the top part, just recurrently, iteratively update the expected value of hidden your hidden values. So this is a deterministically updated using a sigmoid function. So it is exactly the same as what we do with a recurrent neural network. So this part is just a recurrent neural network, but what it differs from recurrent neural network is that the output is a restricted Boltzmann machine instead of just a real valued vector. So if you unfold recurrent temporal RBM through time, you can see this kind of form. So you have this recurrent neural network here, and at each point, your output is this restricted Boltzmann machine instead of real valued vectors. So because once you unfold this through time like this, it can be seen as an energy-based model. So once you know the form of the energy, you can take the gradient of the energy and apply the gradient-based method. So the energy of this recurrent temporal RBM looks like this. It has this form. So it is straightforward to take the gradient for the first several terms, but the last term is different from the standard case. And in this case, so the R is your RNN hidden units, or it is expected value of the hidden units computed recurrently. So it depends on the parameters recursively. So for this part, you need back propagation through time to train your parameters. So the whole model is trained using back propagation through time, but because it has this hidden units which takes random values, you need a contrastive divergence or some other techniques to approximate this expectation with respect to this model distribution. So let's see some example results from of the use of this recurrent temporal RBM. It's been applied to this learning this motion pictures. So this is the training data, and this is a generated time series that is generated by trained temporal RBM or recurrent temporal RBM. It is difficult to see which is a pair, but if you see very closely, this recurrent temporal RBM gives a slightly better movement of this bouncing phenomenon of this movie. Okay, so this is the last slide before the break. But so this recurrent temporal RBM has been extended in several ways. So, for example, this the RNN part of this model has been replaced with LSTM or echo state network, or this in the case of a recurrent temporal neural network, it can be seen as an RNN, but with an output is given by a restricted Boltzmann machine. But this because RNN is the same as the expected value of RBM, the RNN and RBM share parameters. But you can unshare. I think this weight sharing is is from historical reasons, and you can naturally unshare the parameters between RNN and RBM. And this is the work that has been done with this RNN RBM. And it's been quite successful in predicting the next notes of the music sequence. There has also been some extension towards this structured RBM where you have connections only between some particular blocks. Okay, so now we're going to have some break, coffee break of 30 minutes. But so after the break, we're going to continue with this Boltzmann machine for time series, particularly for online learning, how we do online learning. So because the model previously seen requires back propagation through time, so which is not quite suitable for online learning. So how are we going to do online learning for time series model? And in part 4, we're going to see how energy-based model is going to be used for reinforcement learning. So the next, after break, we're going to see more new stuff. So please come back. Thank you.